emphasize
sáng.
again and again that you should keep in mind the sign rule. Like when the object position is positive, when it is negative, also for the image position, so object position, image position, and also the radius of curvature. So that's what we relate to the sign rules. Now we will continue. We will continue our previous class. Yes, so last time I also we stopped here to say that
컴퓨터.
an image formed by one surface or optical device can serve as the object for the second surface or device. So that will bring you to the part of the eye. For example, you have my glass, you see my glass also right. So if you have some defect in your eye and you need to have the eye revision or eye correction, you will need to use another lens. So that's in this part. You will have a lens system. So we will do that right after. Also, you can have like a magnifier or some other optical devices, and in which you will have like this is the image after the first device. However, it becomes the object to the second device. So it is a concept. We will deal with this right after this chapter. So basically today we will finish chapter number 2. So it is our task today. We have here the part of the reflection and refraction at the plane surface. Now we will move to the reflection at a spherical surface. So the first part of this chapter, so I come back to this slide. You have the reflection and refraction at the plane surface, and then we move to the reflection at a spherical one, and also the refraction. And the rest of this chapter, we will deal with the more or less the refraction. So for the lenses, cameras, the eye, the magnifier, and microscope and telescope. So it is what we are going to do. So last time it was a Saturday, and the class like not so many students like today. So that's good. That today we welcome more students to join. So in this chapter, what we need to do is to find the image formed by an optical device. And when we say we need to find the image, that means we need to find the image position. It is first, right? And the second thing is how the image height compare with the object height. So it can be equal, larger or smaller. It can be erect or inverted. It can be real or virtual. So you should keep in mind also the properties of the image. So what we are going to do now also is to find the image of a point object formed by a spherical mirror. Is what we are going to do. So first I will introduce you a spherical mirror. Here we go. Em giúp cô bên bạn em bên mình because we are in the class of optics, sometimes we need to draw follow this course, especially in the part of the geometry, right? So we are in the geometric optics, and you need to draw also. And we use ray to show or to describe the traveling of light, as well as you will use geometry in order to find the image, in order to find the height or the size of the image. That's why we are in the chapter of geometric optics. So what I just mentioned is a spherical mirror. Okay, here. A spherical mirror. So when we talk a spherical object, that means you will have a radius, right? So here, let's have a look as well here. I will use a mouse to show you. So if you have this curve, this one, so you will have this curve here, and C here, what is the name of C? C is the center. Yes, C denotes center of curvature. So you have center of curvature here. And the radius of curvature R. So R stands for radius here. So we are showing you here is a spherical mirror with radius of curvature R. Okay. And if you see this shape like this one, in which the incoming light reflects in this direction, and this shape, so it is a concave. So please show you here the concave. We have concave and we have also convex. So concave and convex spherical mirror. And here we are in the properties of the reflection. So you have concave and convex. For example, this one. Okay. So if you have a point here, and here is the incidence, and then you have the reflection, for example, in this direction. And normally you can use this symbol as well, as you remember well. Right, we can use this as well, or we can have the convex in this place, or you will have this shape, like this one, and the object will be in this position here. So I can move this drawing here. You can use just notation as well, as you like. So here you will have the point at this position. Incoming light. And the center of curvature is here. Here you have the center of curvature somewhere here, for example. So here, C is center of curvature. And also you can have some definition or some concepts related to this mirror. We have the center of curvature of the surface is at C. You see here, C, center of curvature. So keep in mind the concept, center of curvature. You have this curvature and C at the center. Yes. If you draw fully this shape, you will have a spherical object, right? So keep in mind C is the center of curvature here. And you have this point V. V. So V means vertex. So you have the vertex of the mirror is at V. When you draw, you can draw like this shape, or you can use the symbol over there, the notation over there. It's up to you. And we have the line connecting C and V. Here we have CV. So CV is called the optic axis. CV is called the optic axis. Here, CV. You see? So we have like some special point characterized a spherical mirror. C, center of curvature, V, vertex, and CV, the optic axis. And later on we will define also another point named focal point, and the length is focal length. So CV, this length, CV, or the distance from C to any point on this curvature is equal to R, here, equal to R, which is the radius of curvature. So keep in mind, radius of curvature R. The distance from the center of curvature to any point on this surface is the radius of curvature. So that is pretty clear, right? So now, what we need to do in this chapter always is to find the image. So imagine we have a point object P, which lies on also this optic axis. You see here? Yes, so how we can find the mesh? So in order to find the image, we need at least 2 rays. And then we will find the intersection of the 2 outgoing rays from that incoming rays. And then you will find the image. Right? So let's go. You can draw also into your notebook or your draft as you want. So first we will draw PB or PB, yes. So first we will draw a special ray. So P lies on this optic axis. So we will use also directly P come to V. Yes. So if P if this line pass through PV. Okay. So please help me close the door, Zibling. Close the door, please. Thank you. So we have PV here coming to this curvature, PV. So what happened to the reflection ray? If I draw firstly PV like this, PV coming to this curvature, PV, so you see the direction, this arrow. So what is the reflection ray? You please. If we have, so what is the object here? Yes, the object is P, perfect. And the first incident ray is PV. So what is the reflection ray? In order to find the reflection or reflecting ray, you need to draw the normal. Yeah, the main concept we study in the reflection part or the refraction is the normal, right? And the normal here will from C to V, because V is the striking point, and then you draw the normal passing through the incident point to the center. It's also BC, so it's VC, sorry. So it's in the same direction. That's why we have the normal for the first incoming ray, the special one, PV passing through C. You see? So the normal also VC, because the normal to any point on the spherical surface lies between the point and then the center. So it's the same. That's why PV passes through C, strike the mirror normally. So you see the term normally here. That means it's the same with the normal. So that's why it is reflected back on itself. Yes. So here you see PV coming. So this is the direction of the incoming ray. This one. So that's why I always ask you to draw the arrow to show that. So here, and then it will reflect back like this one. The second one. So first, I can draw also on this table. This blackboard. So P coming to V. You see, VC also the normal as well. So here is the normal. It is the normal of this PV ray. So it will reflect back the same. And then we draw also another ray, which is a arbitrary ray, PB. So we call this PB here. Okay, PB. You see. So how can we form, or how can we find the reflecting ray? So you need to find the normal first. So in order to find the normal, here is the incident point. You will connect this incident point with the center. So here. Yes. It is the normal. And then the reflecting ray. So you please You, yes. Please draw the reflecting ray. Đây đúng là thời gian này em lưu ý là đeo khẩu trang để bảo vệ mình nhé, vì đợt này Covid cũng khá căng thẳng. Cô đứng ở đây cô xa cây nên thôi cô không đeo khẩu trang đỡ nói như vậy. Yes, so incoming PB, and I already draw the normal for you, which connects B and C. So where is the reflecting rays? Yes, good. Good. Okay, good. Cool. The direction. Draw the arrow. So where is the image? Yeah, it must be this point because you have the first reflecting ray, VP, and the second one, V something, okay? And it is here. We have P prime. Okay, thank you. So you see, when you have the incoming ray PB coming to the curvature at point B, you draw the normal here, B to C. The normal will be the line connecting the point striking at the radius, the curvature here, and also the center. So you have the reflecting rays in this direction. So these two rays, okay, here. So PD at an angle alpha with the axis. So you see here this angle alpha with the axis strike the mirror at B is reflected at the angle theta prime equal to theta. So you have here this reflection, you see, like what a student just drew here. Perfect. So you can find the image P prime. P prime is the intersection point between this VP and this outgoing ray. Okay, so you have P prime here. And pay attention to this notation alpha, beta, theta here as well, and this is phi. The angle at the center of curvature, we denote this phi. You see here phi. Alpha from the optic axis to this first ray PB, and this is the two angle theta here and here, like the student just denote. So theta, theta, here's alpha, and here's beta, and here is phi. Okay, you have the notation of the angle phi. And if we look at two triangles, PCD and also BP prime C, you can find the relationship alpha plus beta equal to phi. Okay, why? Because if you look at the triangle CPB, we have phi equal alpha plus theta, CPB. And if you look at the triangle P prime CD, or I can say C P prime B, you have beta equal phi plus theta. So for that, for these two relations, you can have alpha plus beta equal to phi. And now, yes, okay, we see here also, you can draw a lot of incident rays, and then you draw the reflection rays. All of them will gather at this point P prime. Okay. And keep in mind that you need to draw the normal, like what I showed you. So the student just drew here. Okay. So all rays from P that have a small angle alpha pass through P prime, forming a real image, because the reflecting rays meet each other, right? So that's why you have a real image. And now we will use geometry in order to find the position of the image. So now we will look at this triangle here. So we will do some more new drawing. You will draw the projection point of B. Okay, you do this perpendicular line to the B from B. And the distance from B to this optic axis, CD, is h. And you have delta here, delta, which is quite small, right? So here from B to this position point is delta. So if you look at this right triangle here, this right triangle P, B, and this position point, you have tangent of alpha equal to h, this distance, right, divided by this distance. So the distance from P to B is s. From P, from the object to the vertex is s. Is the what is s here? What is s?
Đi lâu vậy.
Okay, you please. Yes, you. Yes. What is s on this equation? Showing in the slide. What is s? Here. What is s?
Áp lực.
What is s?
Trên vinh này bạn ấy. Cái gì vậy?
Chỗ này là cô thấy mình nói trò chuyện rôm rả lắm, có tưởng đang làm tán bài, hóa ra là đang thảo luận gì khác ạ.
Chạy xuống.
So what is s? So what is s? Yeah, s is the distance from P to B. So P is the object, and the distance from the object to the vertex of a mirror calls object distance. Yeah, okay, good. And delta here is the distance from the B vertex to this position point. You agree? So we have tangent of alpha equal to h divided by s minus sigma for delta, okay. So it is tangent of alpha. So what is tangent of beta? What is tangent of beta? Look at this figure, because we are in geometry optics class. So we will use geometry a lot in order to find the solution. So tangent of beta equals h over s prime minus delta, okay. Yeah, because you have P prime V minus delta, right? And P prime, the distance from the image to the vertex of the mirror is the image distance. So what is image distance? What is image distance? What is the definition of the image distance?
Như vậy tận cho tôi về quê.
Yeah, but I ask you to translate the term into Vietnamese. I'm asking you what is the definition of the image distance. The image distance is the distance from the image to the reflection or refraction surface. Okay, don't worry. And here we have the reflection surface, and you have the vertex, because we are in the spherical. We are using the spherical surface, so you have the vertex. For the plane surface, all the point is the same. We don't have the vertex. So here, yes. Nhá, các thanh niên nói chuyện trao đổi cũng được, em tập trung vào bài nhé. Hoặc là nói chuyện thì cũng không được gây tiếng ồn, các khoảnh các bạn khác nhé. So you have tangent of beta equal h divided by s prime minus delta. Okay. So it is equal to P from V minus delta. Normally you use the symbol delta like this from the secondary school when you solve the other two equations, right? And so you can use this symbol as well. And you can have also this one, the sigma, delta sigma. I myself always have the confusing between these two. So here's sigma, okay, and here delta. So this from this to here. Yeah, it's very different, but I myself always make the mistake as well. So don't worry. I keep in mind this related to this and this one. So you have tangent alpha, tangent beta, and what is phi? So what is the value of tangent of phi? So tangent of phi, you please, you. What is the equation of tangent of phi? Phi here. So you, in order to solve this, you look at the right triangle. This one, this one, this one.
Thế là bài 6 phần
Yeah. H divided by, yeah, R minus delta, because you have CV minus this delta, right? I do agree. So tangent of phi equals H divided by R minus delta. And in physics, we apply mass a lot, we use mass a lot, and we will use also the approximation. Yes, it's what we are going to do in physics, especially in this part of this. You will consider only the case in which alpha, beta, and phi are very small, or we have the rays, the incoming rays seem to be parallel, right, to the optical axis, or we say the para-axial, okay? And delta is very small compared to S prime, and also R. So that means we have this very, very close, the position of B very close to D. So in this case, when tangent of a very small angle, so it is more or less approximate to, you have tangent of an angle which is very small. So I can say x, for example. X is very small. So tangent of x approximate to sine x and approximate to x. And here we use the unit is radian, radian, okay? So here, alpha, beta, phi will approximate to h over, so if delta is very small, so it's more or less approximate to h over x, right? Here, h over s prime, here, h over r, and then come back to this relation, you will have, okay, we will have this one. 1 over s plus 1 over s prime more or less equal to 2 over r. It's what you already know, right? And learn by heart as well in geometric optics. So here we have 1 over s plus 1 over s prime equal 2 over r. And you have the object image relationship because s is the object distance, s prime is the image distance, and r is the, what is r? You please, what is R? What is R? R. What is the name of R? R. No. Yeah, the radius, because here, we shall write at the beginning of this class today. Okay, come back to the previous slide. Here. R is the radius of curvature from this center of curvature to any point on this spherical surface. You have put it the radius of curvature. So that's why I told you to keep in mind these concepts, okay? So 1 over s plus 1 over s prime equals 2 over r, showing you the relationship between the object distance, the image distance, and the mirror itself, right? That means when you have an object, you place this somewhere before or in front of the mirror, and then you find the image formed by the mirror. And then you see the relationship, how and where the image is formed. You got it? So that's why we have the object-image relationship, depending on the properties of the spherical mirror. Yeah. And last time, or last Saturday, we studied for the case of plane surface. What is the value of R for the plane surface? For the case of plane mirrors, we have the value of radius is infinity. R goes to infinity. So R, 2 over R equal to 0. That's why you have S prime equals minus S. You guys still remember, right? For the plane mirror, okay? Or plane surface, plane surface. When we consider the reflection also, you have S prime equal minus S. Because you can come from this equation. R goes to infinity, so 1 over S plus 1 over S prime equals 0. So S prime equals minus S. And it happens because we use some kind of approximation, as I just told you, in which alpha, beta, and phi more or less quite small. And it happens only when the incoming or the incident rays very close or parallel to the optic axis. That's why we have the case para-axial rays. The rays are nearly parallel to the axis and close to it. So keep in mind this condition here. And you can have also another case in which alpha quite large. So we have the so-called spherical abbreviation, where the image now not like focused on one point, but it can be smeared out here. It happens when alpha is quite large, and we cannot use the previous approximation anymore. Here we go. For example, here you see this picture from some planet, and you see when we do some calculation, we will have the better shape of the image, right? Not like smeared out like this one. Yes. Now we have one special case. Looking at this figure, when you see the incident rays parallel to the optic axis, like this, and all the reflection rays will focus, right, or converge at one point, F here. Yes. So what is the name of F? Here. If you have the incoming rays, or you can use this phenomenon in order to form an experiment. You use the paper and or you have like some spherical mirrors and you gather the sunlight and you will find some point at which the paper can be burnt out, right? So here in this case we have something similar. Incoming rays parallel to the optical axis and parallel to each other. And incoming like this, we have S goes to infinity, very, very far away. And then the reflecting rays focus at this point. So this point, that's why it denotes with F, means focus, yes, focus point. And we see that in that case, if S goes to infinity, so 1 over S prime equals 2 over R. Or S prime equals R over 2. Half of the radius. So that's we have the condition here. And the name of this, we have the focal point and focal length concepts. Yes, so you have here the case of focal point and focal length. Focal point F is the point at which the incident parallel rays converge. You agree? On the incident parallel rays converge to here. You have this case. Or if we have all the rays coming from this point to the spherical mirror, they will reflect parallel to each other. Okay. So you have the concept of focal point. And the distance from this focal point to the vertex here, or the focal point to the center of curvature, will be equal to each other. You have the concept F equal R over 2. Yes, in this case you have S prime equal to R over 2 equal to the so-called F focal length here, focal length. Or in this case, if you have the object positioned at this focal point, all the incident rays to the mirrors will be reflected also in parallel to each other. So in this case you have S prime equal to infinity and S equal to R over 2. You use this object image relationship. Yeah. So focal length is the distance from the vertex to the focal point. Okay. Very clear, right? Yes. So finally in this part, keep in mind the object image relationship. Also keep in mind the concept of focal point, focal length as well, related to radius of the curvature. R is the radius of curvature. C, the point C is the center of curvature. V is the vertex. Yeah. And F is the focal point. Vertex. So here, this point is the vertex. Or we say the most curved point on that kind of curvature from the center. Okay, please also look at these two figures. So you have the concave spherical here, you see, concave mirror. And now I remind you the sine rule. The sine rule. Here you have the incoming ray, and here you have the outgoing ray. And you have here C, the center of curvature. And last time we mentioned if the center of curvature is on the same side as the outgoing ray, yes, we will have positive radius. However, if you look to this second case here, like what I draw here as well, this case you have the incoming ray, the outgoing ray in this direction, but the center curvature is here. Here they are separated by this spherical surface. So the center curvature is not on the same side as the outgoing line or outgoing ray. And we use this reflecting surface as a boundary. And so that's why R here is negative. That's what we studied in the sine rule. Okay, you still remember the sine rule? Who remembers sine rule? S-I-G-N-R-U-L-E, sine rule. Because we are in the geometric optics and sine rule is extremely important. No? Okay. Okay, here. So when the sine rules, yeah, which is the basic, simple but very important, very critical one. We have the sine rule for the object distance. When the object is on the same side as of the reflecting or refracting surface as the incoming light, you have positive object distance. If not, that means the object is on the opposite side of the reflecting or refracting surface as the incoming light, and then you have negative object distance. And for the image, you must compare with the outcoming light. Okay? When the image is on the same side of the reflecting or refracting surface as the outcoming light, you have positive image distance. If not, you have negative image distance. And here, sine rules for the radius of curvature of a spherical surface. When the center of curvature C is on the same side as the outgoing light, for sure we will, yes, outgoing light of the reflecting or refracting surface. The radius of curvature is positive, otherwise it is negative. Okay, so keep in my thought, and now I will show you again. I show you again this figure, this one. Here, so you see, center of curvature is on the same side, right, as the outgoing light, as the reflecting surface. So that's why you have positive radius. Here, the center of curvature is on the opposite side as the outgoing light of the reflecting surface. That's why you have the negative radius. Because when you study like this, it's quite easy to remember. Okay, concave mirror, positive radius. Convex mirror, negative radius. However, if you have the lens, then you must remember the sine rule in order to identify when one or two is positive or negative. So, for this part, it is clear for you? Yes or no? Okay, so now we will see the case, not only a point object, but we will make the more complicated case. We have the extended object. So here. So instead of a point P located on the optic axis, now you will have an object PQ with the height y. Y denotes the height of this object. Yes. So in order to find the image, you also need to draw two rays of light, right? So I will call one student to come to the board to draw that very fast.
Register.
Okay, so I stick this point here. So is there any AMSN student in this class? Yes? No. So you have ICT? No. MST? So who are you? Hematomy bit biotechnology drug discovery. Not HEMAT anymore. You have the new name. DIT. So you're right. Okay, you too. Yes. So you please, the student in black t-shirt. Quick, please. Please find the image of PQ formed by this. Okay, now the student will draw this case. C is here. You please, the student in green t-shirt. Quick. Find the image of PQ formed by that view. So which major you are? ICT, okay. And then here. This one. Meanwhile, please don't forget to draw yourself as well to find the image of PQ. I will come and discuss with you. Today, our teaching assistant, Miss Aida, also has a class, so she cannot join us to discuss with you. Remember, we are in physics or you are in the natural science. You need to write wrong.
Cô vào đây. Ví dụ con vẽ gì đây không? Cái thằng đây là chuyển sang. Cô đang ở đằng sau luôn này cháu. Cháu sẽ chuyển sang. Không thấy chú được. Chú ạ. Sú. Tao sẽ phải đợi sú ạ. Vẫn sú. Nhìn tao không biểu khác nhau. Nhìn tao. Nhưng mà lại có con nào tao không biết. Tao vẫn chưa tải được cái kia của cô xuống. Kia là cái gì? Để chờ. Tao có. Tao nghĩ vậy. Optic đúng không? 2 chắc tới 2. Cô này tên này nhá. Mày cứ gửi ai? Không, từ tao xem nó giống không ạ? Mày gửi ai? Mày cứ gửi cả hai đi. Đấy, gửi cả hai. Đây, qua rồi. Nữa. Đây. Mày. Rồi sao? Đưa đi. Ra lường nhắn gửi yêu thương. Thằng cái thật không dùng được bất kỳ cái gì. Đâu biết tao phế. Ui. Thôi. Sao? Thôi chọn gửi cái ngắn rồi. Mày gửi từng cái một. Ui nhưng mà nó đây có gì? Đây optic này. ngắn hơn một nửa đấy, ngắn hơn một nửa. Cô độc cho đi xuống. Cô độc. Ai đủ. Cô cái này xong. Mày chết. Tao chết. Mày chết, tao chết. Là một người cứ cài lại máy như hiện tại, tôi cứ set hết tất cả mọi thứ ở desktop. Và rồi nó khá là trigger ai đó ở nhà tôi.
CPU Pro là vương còn tức là vậy cả hai trường hợp đó. Chắc vậy. Như cái trang hai trường hợp này. Đây kia là võng mạc.
Yeah, so we have one solution. One solution there already for the case of convex mirror, and I also came to see the solution of our students, and most they are quite good.
Our student.
So first you draw this parallel rays. So here you see where is
Dạ đúng không?
if you
Cái điều gì cơ này. Cái gì cơ dưới này. Tao nhìn thấy tao. Cơ dưới. Tao nó cơ dưới. Cái điều gì đây. Cái điều gì đây. Cơ dưới.
Ngã xuống rồi.
Chịu.
Bắn thế gì rồi?
so you understand how to find the image.
CPU
So we have the solution on the board, and also you see here on this slide we have also the image. So for example, for the first case, you have a concave mirror, which is we have the focus point here, the center curvature is
cái
here,
chẳng tiền à?
the focal point
Nhưng mà nó
is right at the middle of the CV, and your classmate drew the first rays come from P parallel to optic axis. Parallel to optic axis, so it reflects through the focal point. You agree? Okay. And also the second special rays you should use is the ray coming to the mirror,
Google
passing by the center of curvature. Center of curvature. So in that case, the normal will be on the same line, and then it reflects back. Yes. So that's why you have two reflecting rays meet each other at P prime, Q prime like this one. And these two reflecting rays meet actually, or meet in reality, right? So that's why you have a real image. So the image is real. If you use the drawing, you see that the image is real. And what is the direction of the image you see here? Yeah, opposite, or we will say inverted. Yeah. Last time you have the concept inverted. If we just draw it, then you can find this. So, real, inverted. And another case you can have is virtual and erect as well. You will see. It can be larger or smaller than the image also, and than the object also. But we can see this case is smaller, right? Smaller. So what we use from the drawing is that smaller than the object. Now we will have a look for the case of a convex mirror. So here we have the center curvature is here. So here is vertex as well. So normally you should you should specify center curvature, vertex, and also the focal point is what we should have. And now we look at the solution. He draw PV. So if you draw PV, the incident rays, so the normal will be the optic axis. Yeah, because B and C lie together, you have the normal. So I write here, normal. So that's why you have the reflecting ray symmetric to the optic axis for the first case. The second rays he used also one we say like okay, I see what he draw. So he draw the incoming ray parallel to the optic axis. So in that case, the reflecting rays pass by the focal length, focal point. So here I can correct a bit for him is that it should be F, not C. You understand what I mean? If he draw like this one, however, if you draw like this, C is over there is not so kind like correct line. So pay attention, F here. I think this student made some kind of confusion. Because if you draw like this one through F and then you draw another ray like this, I don't understand why you draw like this one. So here, you think it is F, the focal point, or the center of curvature. If it is the center of curvature, the rays does not go this way. It can only go this way if it is the focal point. Okay? So I will erase this line. Imagine, okay, we can assume that this is the focal point. So here, reflect like this, and all the rays behind the convex is in dash like this one. So that we have the meeting point is here and here, so you have P prime, Q prime. So in that case, C somewhere here, okay, I can say C somewhere here, okay? So in that case, the image, the properties of the image is, it is real or not real? Not real, right? So we don't say fake like last time I told you. You will say it is virtual. And if you look at the direction, it is the same direction, so we say erect. Yes. And also smaller than the object. So we have two examples, and here showing you in this slide. Also, you see, the object is here. You draw the first ray. The first ray passing through the center curvature, so coming to the spherical mirror, it will reflect back because it's aligned on the same the normal here. The second ray you come from Q to the vertex, so it reflects symmetrically to this ray of the optic axis. So the two reflecting rays meet each other here at this point. So you have P prime, Q prime with the height Y prime. So you understand how to form the image, right? How to form the image for grid. And the position of the image is the same. We will use the previous formula or previous equation, 1 over S plus 1 over S prime equal 2 over R or equal 1 over F. Yes. And in the case you have an extended object, so the height of the object, when the mirror formed an image, will be changed. So we see here a concept which is described, the ratio of the height of the image compared to the height of the object. So it is a so-called lateral magnification. And for the plane mirror, what is the value of M? For the plane mirror, what is the value of M? M equal to 2 minus 1. to minus 1. We have exactly m in that case equal to 1 because it's equal to minus s prime over s. And last time you have s prime equal minus s. That's why you will have this. And in this case you have this definition, lateral magnification m equals y prime over y equals minus s prime over s. And m can be positive or negative. If m is positive, we say that the image is erect. Yes, in the same direction as the object. And if m is negative, we say that the image is inverted. Yeah, another direction. Yes. So in this case, you see, for sure you have the real image. So s prime is positive.
Nghe tôi mơ.
So m equal to minus s prime over s will be negative. So that's why you see inverted direction here. Okay. So my dear students, you understand how to form an image by this spherical mirrors, by reflection. Okay. For a point of an extended object, right? We have also one example. However, you can do this later at home as well. What I just asked you to draw there, also an example, and you do yourself. Right? Okay. And now we move to the convex mirrors. Last time we just have also focusing on one case is the concave mirror. However, I also asked you to draw for the convex mirror. So the convex mirror here, very similar to the concave mirror. Here, you see, the center curvature is behind the spherical surface. Or we see that it is on the opposite side as the outgoing ray of the reflecting surface. That's why you have negative radius of curvature. And also, you use the same formula, 1 over s plus 1 over s prime equal 2 over r, and you have the same formula for lateral magnification for the concave of the convex. And you know how to draw for the case of convex mirror, right? Okay. And the focal point, yes. In this case, you see, if you have the incoming rays parallel to the optical axis and the reflection like this one, so actually they don't meet each other. You need to do the extension, right? So that's why you see the dash line. I always ask you, if it is not real, please use the dash. Here, dash. If it's real, you use a solid curve. So solid and dash. Okay? So pay attention as well. So that's why you have the virtual focal point. We don't say fake focal point, you use virtual focal point behind the mirror. Okay. And if you have the incoming rays here, the incoming ray, they have the extension passing through F like this one. Okay. And they will reflect back parallel to each other and parallel to the optical axis. Also, you have focal length the same, f equal to r over 2. And pay attention, for the convex mirror, you have negative r. And the reason why r is negative, we use sine rule, and I explain again and again to you. So for sure, it is well noted. I do hope that. Okay, right. So we will have a graphical methods for mirrors. So you have this spherical mirrors, and what is the name of this one? Oh, perfect in Vietnamese. And in English, what is the name of this mirror? You please. A concave. Yes, it is a concave. Okay, concave. And we have 1, 2, 3, 4. You have 4 special rays. So you see 1, 2, 3, 4. Even this rays as well. The rays also from P, but we will pay attention to the point Q of this object because this object is perpendicular to the optic axis. So we will find the image of Q, and then we just make the perpendicular line, and then you have the image P prime, Q prime. That's why you will have 4 special rays. Let's go. So the first ray, please describe the first ray. You please describe the first ray. Yeah. Please describe the first ray. Yeah, please have a look and then just describe it. The first ray, the first incoming ray, parallel to the optic axis. Yeah, optic axis. It reflects
around the fold.
Yeah, it reflects through the focal point. Okay, good. The second rays, please. The second special rays.
It reflects part of the focal point.
It does not reflect through the focal point. Here, the second rays passes through the focal point, right, to the spherical mirrors. It reflects parallel to the optic axis. Good. And the third ray, please transfer the mic to the student behind you. The third ray, please. Please describe the third ray, the third one, in orange.
It goes through the center.
The center of curvature. Yeah, the center of curvature. V-A-T-U-R-E. Center of curvature.
And the reflex ray is also goes through the curvature.
Yeah, so it reflects in the same direction, right? In the same direction. Proceed. And the fourth ray, please also transfer the mic to the student behind you. The fourth ray, please. The fourth here. What is B? Vertex, yes. So if the incident rays strike the mirror at the vertex, it reflects. What is the direction here? It reflects symmetrically, right, to the incident rays through the optic axis, or it reflects at the same angle as the incident rays. You see? Yes. Similar to the case of the, what is the name of this mirror? Convex. Yes, so C-O-N-C-A-V, concave, and here convex, V-E-X, okay, the same. So finally we have the principal rays. Thank you, please turn off the mic and then I will ask you later on. A ray parallel to the axis, after reflection, passes through the focal point, you see, passes through the focal point F of a concave mirror, or appears to come from the virtual focal point of a convex mirror. Because you see here, it does not pass through the focal point of the convex mirror. So we say it appears to come from the virtual focal point of the convex mirror. You see here. That's why you need to use the dashed line behind the mirror. The second one, a ray through the focal point. Or in the case of the convex mirror, you see a ray proceed toward the focal point F. Is reflected parallel, you see, parallel to the axis. But the axis or the full name is optic axis. The third one, a ray along the radius or away the center of curvature. Okay, they intersect the surface normally and is reflected back along its horizontal path. Finally, a ray to the vertex B. Here, a ray to the vertex B. A ray to the vertex B. is reflecting, forming equal angles with the optic axis. So there are 4 special rays you need to keep in mind to draw to find the image, and you need only 2 rays in order to find the image. So very clear this part, right? Yeah. For this example, you can do yourself at home. Okay. Here we have some different cases, different situations. The distance here is larger than the radius curvature in this first case. The second case, you have the distance or the object distance here. The object placed at the same of the center of curvature. The third case is when the object located at the focal point. And the last case, you have the object located here between the focal point and the vertex V. So you will see the change of the image formation. Here, real, inverted, and smaller, right? Here you have real, inverted, and same size or same height. Here you have infinity image, and here you have vertical, erect, and larger than size of the object. So you need to draw these dots. Now we will move to the next part, but we will spend 5 minutes of break, okay? Chúng ta sẽ quay lại lúc 2 giờ 15 và các clip không nóng đấy. Các clip nóng không ta?
Có.
2 giờ 15 nhanh nhé.
Xong hết rồi. Đủ người rồi, phân việc rồi. Làm xong một giờ rồi. Vào cái văn đó. Đúng không? Đúng là cái này không? Cái này thì là Nguyên Văn Bờ à? Ừ. Ô! Ôi, nhóm 5 thằng rồi. Sướng. Biết ai làm. Mày nhóm tao nhắn từ buổi sáng rồi, ai còn chưa xin. Chết. Tắt ôn vào. Tắt hết rồi. Thế cái bàn này có gì? Em cùng quay à? Hiện tại em hết dung lượng rồi ạ. Em cùng một tại không quay cái này. Em cũng muốn quay. Em quay à? Quay.
Đây các bạn.
Như một cái sách.
Được.
Mày chết.
Tao chết.
Không mày biết nào. Có này cho mình không? Trong đây. Ồ, ông này ở trong cái nhóm VVUSTH. Ông này cho mình không? Ừ.
Việt.
Con
Việt. Tao một hộp. Ê thì thôi ơi. Lưu mày cũng như lưu của tao. Đây là vừa làm ôi trời ơi, bây giờ tao còn mấy đâu chẳng được nhóm sao. Ô đây nhóm 6 này. Nhóm 6 ạ. Bao giờ nhóm mấy? 7. Nó bay đâu? 3. Tâm đã có Google mà. Nghĩa là nó vào đúng cái nhóm mà có tất cả thằng nó biết nói chuyện hết. Năm mấy? Năm mấy quan trọng. Tôi hỏi thôi. Cứ hỏi là tôi cứ hỏi đi. Tao không thích trả lời. Nhưng nói đi. Tao nói gì? Tao nói gì? Tao nói. Không tao nói. Không biết không? Tôi đang phải thành viên nhưng mà cái đấy thằng nào mà đau hơn. Có thể nó xấu. Điện thoại dùng điện thoại chứ. Con tìm 4 thằng rồi, còn một thằng cùng muốn cấp lại.
file đấy. Tôi tách từng file code ra một để chỉnh sửa cho tiện.
Mày làm hết rồi hả? Mình mới làm.
Mấy cái đã xong rồi nên là tôi làm là phần của tôi. Hát người nhóm ông à? Nào, bây giờ đi gánh bài 2 nào. Nào, chúng ta cùng bài 2. Có gì không? Mày nói chính mày à? Đúng rồi, mày nói chính mày à?
Thì nó đang bảo cho nó mà. Cả trường sẽ biết mày là mùi nghiện cái thôi.
Có thật giả vờ rằng mình không chơi game với bạn này có thế chúng ta kéo nghĩ được cái giờ đấy luôn. Đầu tiên chúng ta vẫn còn copy cái mic và cái sự quang đã rơi vào trạng thái trầm tư, hướng nội quanh.
Okay, so we can come back to the class. So F, focal point, and the distance from focal point to the vertex is focal length, and you have the distance from C to vertex is radius of curvature, and focal length equal to half of the curvature. So during the break, also I received some questions from students, and we also discussed together. Now, we finished this one already. We go to. So we just found the image formed by a spherical surface by also the phenomenon here is reflection, but also you can have the refraction. If the spherical mirrors split our media in two different materials. So please have a look here. Reflection, so you will have the bounce back. That's why you have the reflection. If we see the incoming rays and then you see this part refract or transmit, also you have here is the image, a point object by a spherical but refracting surface instead of reflecting surface. So pay attention, you have reflection and refraction. So in this case, we will focus on the refracting phenomenon. So you have this spherical surface. We have this spherical surface, and here C is the center of curvature, V is the vertex, and you have this point P located on the VC line, and VC line is the optic axis. Okay, sometimes we call axis. That means the optic axis. In order to find the image of the point P, we will draw at least two rays of light. The first one, which is the simplest one, you draw PV, see here. So if the rays of light coming here, PV, so you know that the normal also on the same direction, so that's why you have it pass like this one. The second medium, okay. The second ray that we will draw is PB, or we have like an arbitrary ray. And any ray, you have PB. So in order to find the refracting rays, what we need to do is to find the normal in the second medium. So what is the normal here? So you please transfer the mic to the student behind you. Yes. So tell me, if we draw PB, the incident ray, now we need to find the refracting ray in the second medium. How we can find the normal? How we can find the normal? Because we want to draw the refracting rays, we need the normal line, and then we use which law in order to find the refracting ray? Which law? What is the name of the law we studied last time? Snell's law, right? Snell's law. The Dutch scientist, Snell's, S-N-E-L-L, Snell's law, showing that NA times sine theta A equal NB times sine theta B. So you please, what is the normal here? The normal. You understand the concept of normal? Normal. Normal. N-O-R-M-A-L. Normal. So the incident rays PB, in order to find the normal, because we have the spherical mirror here, and which is the spherical refracting surface with the center of curvature C here. So you will just connect C, the center of curvature, and B. It is the normal. Okay? So here you have this line is the normal you see here. And theta A is the incident angle. Theta A. Theta A is the incident angle forming from the normal to the incident ray. So you have theta A, the angle in the material A. So you have material A and material B. With NA and NB, what is the name of NA? What is the name of NA? You? What is the name of NA? Use the mic and please answer me. Use the micro and tell us the name of NA. You don't remember? Yeah.
It's a refractive index.
Yeah, good. The refractive index of material A, or we say index of refraction. In Vietnamese, like Đức Lâm, right? Just answer. So you have NA and NB, and here's theta A. So in order to determine theta B, we see that in the case we have here NA smaller than NB. So using Gauss law, using Snell's law, you know that theta B smaller than theta A. That's why we can draw the refracting rays like this one. You understand what I mean? Okay, so that's why you have this refracting ray and the two outgoing rays, this one and this one, meet each other at this point, and we call that P prime, which is the image of P. Here we denote alpha, here we denote beta, and here we denote phi, similar to what we just did in the part of the reflection. And we also draw the collision point of B. You put this line perpendicular to PC here. We have the distance is h, and we have this small distance is delta, very similar to what we just studied. So in this case, we have a spherical surface with radius r. So from C to this point, we have the radius r, and which separate two materials with refractive indexes, NA and NB. And in this case, we consider NA is smaller than NB. Okay. P prime is the image of the point P, and I just described to you how we can find the image. So here we have the image P prime of the object P formed by refraction of this spherical surface. And in this case, we consider the refractive indexes of two materials, NA and NB, and NA is smaller than NB. If NA is larger than NB, and then we will have another direction for the refracting rate, right? Okay. So what we need to find in this part is the relationship between object distance and image distance is what we need to do through this chapter as well. So we draw first PV strike the sphere, so it will pass straight into the second material. So I just explain also because CV is the normal and also the same line as PV. So that's why you have the refracting rays go straight. The second one, PB, is incident at the angle theta A. So the angle incidence is formed between the normal here, please see my mouse as well, and the incident ray. So we have theta A. And it is refracted at an angle theta B, formed by the normal to the refracting ray. You have theta B here. And the relationship between theta A and theta B, I just tell you, is Snell's law. Snell's law.
Từ từ chưa biết là số lượng bao nhiêu ấy, nhưng mà hiện tại ít nhất là có 5 thằng.
So Snell's law shows the relationship between the incident angle and the refractive or refraction angle. So what is this one between theta A and theta B and A and B? Snell's law. Okay, you please. Snell's law, do you remember? Snell's law. Snell's law. When you study physics, please remember the names of the law. To respect the scientists who discovered, who invented or proposed the law. So Snell's law, you have theta A, theta B, and A and B. The relationship is NA times sine theta A equals NB times sine theta B. So if I write like this, you remember, right? Okay, to show you the relationship between the incidence angle and the refraction angle. So these two intersect at P prime, and you have object distance equal PV, image distance equal P prime V. The object distance is the distance from the object to the vertex. From the object to the vertex. And the image distance is the distance from the image to the vertex as well. Now let's go. We have in this case S here, S and S prime, and also R. All of them are positive. Why? Because here the object also on the same side as the incoming rays of the refracting surface. You agree? So positive object distance. S prime, so you have the image here on the same side as the outgoing ray of the refracting surface. Hai bạn nam ngồi ở cái dãy đầu tiên đấy, hai em đấy, nếu các em mà ngồi cảm thấy rằng là mình nói chuyện to hơn cả cô nói, các em cứ ra ngoài nói chuyện, đỡ ảnh hưởng cả lớp. Các em có thể học cũng được, không học thì nhưng các em không bị gây ồn nhá. Các em làm gì cũng được, cô không có can thiệp đến việc các em ngồi trong trường làm gì, nhưng tốt nhất các em đừng gây ồn. Đấy là phép lịch sự tối thiểu ở trong lớp. Cô nói tiếng Việt rõ nghĩa nhá, em lưu ý. Cho các em làm gì được whatever. However, please don't disturb others. And now we will explain why R is positive. So if you look at this refracting surface, we see the center curvature is here, right? So the center curvature also on the same side as the outgoing rays of the spherical surface here. So that's why are also positive. So please keep in mind the side rule, and I just repeat again and again. So now we will see what is the relationship between object distance, image distance, and also the property of the spherical surface, which is the radius of curvature r. Okay? Like what we just did in the previous part for the reflection. So we will consider the triangles PBC. Okay, look at this triangle PBC and P prime BC. So we will see the relationship of the angles. So we got PBC. So we have this angle is something like the external angle of B, right? So we have theta A. Theta A equals the sum of these two angles, alpha plus phi, right? Yes, you have this relationship because the total of the three angles inside a triangle is equal to 180 degrees or equal to pi. So that's why this angle also is equal to the sum of these two other angles inside a triangle. Also, if we look at this triangle P prime B C, we have very similar phi equal to beta plus theta B. Yes, so you apply these two relationships. Also, the Snell's law I just recalled here. You have NA times sine theta A equals NB times sine theta B. And we consider the case in which alpha, beta, and also theta, phi also very small. So you have the approximation here. Sine theta is approximate theta. So we can deduce that from Snell's law you have NA theta A equal NB theta B. Okay. So you can deduce theta B, the angle of refraction in the second medium equals to the NA over NB times alpha plus phi. And then you can use also NA times alpha, you replace also the phi by beta plus theta B, and you change the sign of these two. You have NA alpha plus NB beta equal NB minus NA times phi. And now, if we do also the position like we did in the reflection part, you see tangent of alpha and tangent of phi and tangent of beta. So what are they? So you have tangent of alpha because you need alpha, beta, and phi. So we need to check what is this. Tangent of alpha, you look at here, equal to h divided by s FPV plus this sigma. Sorry, this is delta. Okay. I told you I will also sometimes have the confusion between the symbol delta and sigma. So tangent alpha equal h divided by s plus delta, and tangent of beta. So you look at this right triangle, P prime B and the position of B. So it equals h divided by s prime minus delta. Okay. And tangent of phi equals h divided by CV minus delta. So it is r minus delta. And we consider all the angles are very, very small. So we will have alpha equals h over s, beta equals h over s prime, phi equals h over r, similar to what we just did. So now you replace into this formula from here to here, you will have this relationship NA over S plus NB over S prime equals NB minus NA over R. So this is the object image relationship in the case of spherical refracting surface. So you have this formula showing you the relationship between the object distance, image distance, the radius of curvature of the spherical surface. And also for sure, very important is the refractive index of two materials, which the spherical refractive surface splits the medium into two. Okay, so we have this one. So what we just did is to prove this formula. And you see we can use geometry in order to find that. Very simple. So, you understand this? You understand that? Okay. Now we will see the case, not only the point object, but we will extend to the extended object here. We move to the extended object. So now you have an object called PQ here with the height y. So what we need to do, you will need to find the image of Q. And then we will do the perpendicular line. You have the image P prime, Q prime. So I can describe as well, and then you can draw into your notebook also. One special ray is the ray in which the rays of light pass through the center of curvature. Because if you draw this rays, it will go straight. And why it goes straight? In the second medium, yes, we draw this rays from Q passing through to C, and it will go straight. And my question is why it goes straight? Why it goes straight? Any idea why it goes straight into the second medium? If we draw this from Q coming to this, and this color and this color to show two different materials. Q to C and go straight. Because in the second medium, in order to find the refracting ray, you need to draw the normal. Please keep in mind the normal. So here, see, and this point the same. Also the normal is here. That's why it goes straight. You understand that? The second one you should draw is QV. So if you draw QV, the rays coming from Q to V in the first medium, and now in the refracting medium. What is the normal? The normal is CV, right? So here is the angle of incidence, and because NA is smaller than NB, that means the angle of refraction is smaller than angle of incidence. So we will draw a rays like this one, in which theta B is smaller than theta A. Okay? So you have two refracting rays meet each other at this point. So this point is the image of Q. We have that Q prime, and then we have P prime here with a perpendicular line. So P, Q, P prime, Q prime, PQ with the height y, P prime, Q prime with the height y prime. And if you use the drawing, you see that they are not in the same direction. So the image here is, the first property is real, right? Because the two refracting rays meet actually. The second, showing the direction, they are inverted. And the object is smaller than the object. The image is smaller than the object. Yes. So, pretty clear, right? And in the part of the extended object, you will have the concept of lateral magnification for the point node. Yes. So also the same, the lateral magnification, showing how the image is changed in the term of height compared with the object. Yes. So we have lateral magnification M equals y prime over y equals minus, but now it's not S prime over S easily anymore, but you have NA times S prime over NB times S, because it's related to the two medium. Last time you have only one medium, so you have minus S prime over S, but in this case you have also NA and B as well. Okay? So you must know how to find the image Yes, and the equation, what we study during the lecture is to prove also the equations. But if you don't understand how to prove, it's a little bit sad. But at least you must remember or learn about the formula. Yes, what show you the relationship between object distance, image distance, radius of curvature, the refractive index of two materials. That's why we have the refractive surface
Cái đó là
here.
phần trăm, cái tại không trăm chắc cái là một phần trăm.
Here we can have also this case P prime Q prime here, but this case you have also n is smaller than n. So P prime Q prime is an image of an extended object P. We have this case. We got QV tries the sphere at the angle theta A, so it refracts at an angle theta B. You see here, okay. QC is incident through C. So it refracts along C. So I just explain because we have this line, so the normal, and here the normal is CD for the case of QB. So they intersect at this point Q prime. So that's why you have the image Q prime B prime. We will do the proof as well. Like we consider the triangles PQB, PQB, and P prime, Q prime, B prime, because it will show you the relationship between the height of the object and the height of the image. So you got tangent of theta A here equals y over the distance here BD is s, and tangent theta B equals minus y prime over s prime, because you see the different directions, so that's why you add the minus here, or the negative one. And we apply Snell's law because we are in the refraction. So NA times sine theta A equals NB times sine theta B. And also the angle is small, so you got the approximation, tangent and sine approximate to each other. So you can deduce here NA times y over s equals minus NB over NB y prime over s prime. That's why you have here n equals y prime over 1 equal minus NA over NAS prime over NBS. That's what we can prove this. And for you to solve the exercise or the question, you just learn by heart this one. And how we can prove that, we already did using geometry. Again, I note that with you. Yeah. S is the distance from P to B, so that's why it is the object distance. The S prime is the distance between P prime and B. B is the vertex of the spherical mirror, that's why it is the image distance. Okay? Yes, so this is the lateral magnification, because later on we will study also angular magnification. Okay? So here the lateral magnification formed by the spherical refracting surface. So last time you have also lateral magnification, but for the spherical reflecting surface. So the difference between reflection or refraction is that reflection one medium, refraction two different medium. Okay. So then we come to the plane refracting surface. So in that case, R go to infinity. Yes, R go to infinity. So you will have NA over S plus NB over S prime. Instead of NB minus NA over R, it will go to 0. And then you have N equal to 1. Yes, for this same lateral size and erect as well. We have an interesting example. However, you need to do it at home. You cannot have enough time to solve it now. And in the lecture note, I also send you the solution. Do yourself and check that as well. Now we will move to the thin lenses. Thin lens, so we will see also the glass here, thin lens. So showing you here is the figure of the thin lens. Okay. So the definition of a lens, so a lens is also an optical system, but with two refracting surface. But so you see, you come from one spherical refracting surface now in two,
thập đủ các khuôn
and
cỏ
then
ấy.
these two
Cùng hệ
from
với
here,
nhiều hệ
this one
hiện tại là đang
refracting
người đầu
surface,
tiên
this
đủ
one,
hệ.
these two form view a medium. We have called that here the lens. Yes. And the thin lens, it has two spherical surfaces close enough together that the distance between them, or we say the thickness of the lens, can be neglected or very, very small. So very close, and we can ignore that. So that's why normally you can use this symbol to show a thin lens as well. Here you can use that, or in your drawing you can use this one. Okay. I see you agree with me. So here is F1, F2. And this one we have one type of the lens. And also you will have another one in which the edge, in this case the edge is smaller than the center, right? And also you have another case in which the edge is thicker. For example, you can have like this shape. So that's why you will use this red drawing. Okay, you have this one. And in that case, we don't say F1, F2 like this. We will denote here F2 in this side and F1 in another side. The order of the focal point is different. So here you have the first case of the thin lens. Okay, so now we will have a look at the properties of the lens. And I recommend you, when you draw, you can draw using this symbol, like
Chắc nó lên đến 6 của một phát được.
Không lên đến 6 nữa.
Yeah, it's easier. So first is a converging lens. Why it is named or it is called converging lens? Because if you send a parallel rays coming to this thin lens, you see that the outgoing rays converge or gather at one point. So that is called converging lens. Easy, right? Here also, so here we call that the F1, F2 the first focal point, F1 and F2 the second focal point. We define the focal point. The first one is that the rays of light coming from the first focal point to the lens will refract, you see, in parallel to the optic axis. And here, the incoming rays parallel to the optic axis will gather or converge at the second focal point. So we have the case of converging thin lens, in which the focal length, the distance from F1 to this point, normally we call this center point is O. Normally you call here O is the focal length here, and focal length in this case is positive. So for a converging thin lens, a beam of rays parallel to the axis passes through the lens, and the rays converge to a point F2. And rays passing through F1 emerge from the lens as a beam of parallel rays. So that's what we have in converging lens. So F1, F2 are called first and second focal point. So you see, because they focus the light. And small f here is the distance from the focal point to the center of the lens is called focal length. So if you understand well the part of the spherical surface, then we move to here. It's very simple. Yes, that's why I discuss with you very slowly, very detailed for the previous part. I do hope that even you are very sleepy, I do really understand well. However, you got some knowledge of the office also. And I understand as well that we need to talk to each other so that you don't feel sleepy anymore. However, please don't make noise, okay? This line connecting the centers of curvature. Center of curvature. So here, this curvature, the center is somewhere here, and here, the center of curvature is somewhere here. And this line, it is called optic axis. The line connecting the center of the curvature to spherical surface is called optic axis. Clear? Right. For the definition of the converging thin lens. And for sure, our task is to find the image. Yes, so we need to find the image position or equipment. So we got PQ. Yes, an object, an extended object with a height 1. And you have here the converging lens. And O, as I told you, the center of the lens will be denoted as O. So you should draw the first line. Yes, the first line parallel to the optic axis, so it will passes through the second focal point. Okay, and also you draw the line passing through the center of the lens and draw straight. Okay, yes. So these two rays of light meet each other at this position. Or you can draw also PQ at 1. The laser is too bad, I will draw here. So you can draw also Q at 1. And then it will go parallel to the optic axis also. Yes. So S is the distance from the object PQ to this O, this point O here, or the object, we say the lens, is the object distance, and S prime, the distance from the image, P prime, Q prime, to O, because the object and image distance, S and S prime. And Y here, the height of this object, and Y prime, the height of the image also. So you have Y and Y prime as the object and image height. So you can draw QA parallel to the optic axis, so it passes through the second focal point. Okay. Q prime passes undeflected straight through the center of the lens. So there are two special rays you should use. Now you will prove again what you know before. So you still remember the relationship of the object distance and image distance for the lens. You study a long time ago, and normally you will denote D prime, right? So you have 1 over D plus 1 over D prime equals 1 over F. Yeah, this is what you know so far. Now we will prove this. But we use S and S prime, not D anymore. It's just the notation. You can use whatever you like. Even in this class, you can use S or D as you like. So, in that case, we will consider these two similar triangles, PQO and P prime Q prime O. So you see these two angles opposite to each other, so they are equal to each other as well. Okay, but they are only similar triangles. They are not exactly the same. So they have similar triangles. So you have PQ over P prime Q prime equals PO over P prime O, right? So you got Y prime over Y equals minus S prime over S. The reason why we have the negative or minus sign here is that Y prime and Y are opposite direction. So that's why you have the negative symbol here. And now if you consider the similar triangles OAF2, OAF2, and P prime, Q prime, F2 as well, these two. Okay, so this couple triangles. So the same angle here, F2 is beta. So you got Y prime over Y equals to the distance here is P prime F2 divided by F2O. So that's why you have S prime minus F over F. Yes, because here is S prime, so and here is F, that's why this distance is S prime minus F. And you have this negative sign because Y prime and Y are opposite for image and object direction. So you can deduce these two by this formula, what you know from you are a kid, right? Now you are 18, so you go to an adult. Now, so you can prove that 1 over S plus 1 over S prime equal 1 over F, and it is the object-image relationship for the looking lens. Yes, so it's the same for the case you have before, just like 2 over R, right? And M equals Y prime over Y equal to minus S prime over S. It is the lateral magnification of the thin lens. Yes, so we can have that. Because this part we already knew, so I also be faster. A diverging thin lens here, you see. The edge is thicker than the center. And if you send a parallel rays of light to the optic axis, we see the outgoing diverge. So that's why we have the diverging thin lens. So the properties of a diverging thin lens is that a beam of rays parallel to the axis passes through the lens and the rays diverge to the point at 2. So you see here, the outgoing rays in fact diverge and they seem to meet at 2. That's why at 2 is virtual and is located here. So now you understand why for the converging thin lens you have at 1 and at 2, but for the diverging thin lens, remember the image focal point located here. That is the reason. That's why at 2 is here. Because to define the, we say like the image focal point is that you send a parallel rays of light to the lens, and then how it goes together, you will have the image focal point. So the rays divert to the point at 2. So you have the second focal point is here, and you have the first focal point is here. If you send this rays of light, seems to gather at this point and it goes parallel to the optic axis. So this point is the first focal point. The incident rays converging toward the first focal point, you see, converging towards the first focal point, F1, and then they emerge from the lens parallel to the axis. So that's why the first focal point is here. We have different ties for the face of this lens. You can have the converging lenses with this shape. Double convex, plano, so you see plane here, so plano convex, and here mini crest. Okay, and for diverging lens, you can have double concave. So you see convex, and here concave, and here plano concave and mini crest. So please don't make a mistake between the convex mirror and this thin lens. Okay, you can be confused between these two. Any lens that is thicker at the center than its edge is a converging lens, is a positive focal length. And any lens that is thicker at its edge than at its center is a diverging lens, which is negative. It has negative F. Okay. Now we will also see what is the value of the focal length and the refractive index of the material which creates the lens. Also, so we go to the part of the lens maker equation. Yes, lens maker equation. So here we have a mini crest here. You have this object, you use the reflection in order to find the image. So you have two refracting surface, like that, this one and this one. So from the first one, you can find the first image P prime Q prime. But this image P prime Q prime becomes the object to the second surface here, and you finally find the image P2 prime and Q2 prime, or P prime prime, Q prime prime here. So you got here S1 prime, you see? So S1, the object distance from the object to the first spherical surface, and S1 prime from the Q prime to the first surface. Also, it is the object to the second spherical surface. That's why you have here S2. And here you have S2 prime, the image distance to the second spherical surface. And you have NA, NB, and C. NA denote the material here, and B denote the material formed by these two spherical surfaces, and then C is the material in this direction, in this side. So Na is the material in which the object is located, and B is the material in which the first image P prime Q prime is located, right? And also it is the object for the second spherical surface, and the NC is the material of the final image. Okay, here we go. We will find the relationship among the focal length F, the refractive index N of the lens, and the radius. So we have here two spherical surfaces. So we have the radii of the curvature R1 and R2 of the lens surfaces here. Yes, so we draw here from, and then it becomes also the incident rays to this. And you have here C1, C2, the center of curvature of two reflecting surfaces, and you plot R1 and R2 here. So we have two spherical interfaces, C1, R1, and in which C1 is the center of curvature, R1 is the radius of curvature, and C2, R2, separating three materials with refractive indexes you see here, Na, B, and C, as I just described. And S1 prime as the object and image distances for the first surface. S2 prime as the object and image distances for the second surface. That's why at the beginning of this class I recall you the case in which one object can be, or we say that one point or one object can become the image of one object device, but it also is the image to another one, so vice versa, relation. And the thickness, here you see T. You see T? Yes, very small number and quite difficult to see, but it is T. Here the thickness of this part, T, here, is quite small. Very small compared with S1, S1 prime, S2, S2 prime. So you have the relationship between S1 prime and S2 is that S2 equals minus S1 prime. Because you have S2 is equal to T minus S1 prime. Yeah. So you use this relationship for the first material. S1 prime, you see, is in the material B. So you got Na over S1 plus Nb over S1 prime equals Nb minus Na over R1. So this is the formula we found from the spherical refracting surface. Yes, for the couples materials here is Na and B. And now we will see similar for Nb and C. We got Nb over S2, yes. Because this P prime, Q prime also the object for the second spherical refracting surface. So you got Nb over S2 plus Nc over S2 prime here equals Nc minus Nb over R2. So you use these two relationships we found earlier, and here we consider Na and Nc are air, and B is the material of the lens. So we consider Na equals Nc equal to 1, and then B equals N. We consider that as well. And you got the relationship here, S2 equals minus S1 prime. So we can deduce, yes, you can replace into these two equations, and you can find out one. You replace Na and C equal to 1, so you got 1 over S1 plus N for Nb equal S1 prime equal Nb equal to N minus 1 over R1. And here you replace S2 by minus S1 prime, you got minus N over S1 prime plus Nc over 1 here, 1 over S2 prime equals 1 is Nc minus N over R2. And then you see N over S1 prime, N over S1 prime the same. So if you plus or you do the sum, side by side these two equations. Yes, sound. So you neglect this part. You will get 1 over S1 plus 1 over S2 prime equals, you make n over 1, n minus 1 as the mutual element out, and then you will have 1 over R1 minus 1 over R2 in the middle. And if we consider this system as like PQ is the object, and P prime prime, Q prime prime is the final image of this length with the material n, you can deduce that 1 over S plus 1 over S prime equal n minus 1 multiplied by 1 over R1 minus 1 over R2. And 1 over S plus 1 over S prime equals to 1 over F. You remember? Yes. So you will finally have 1 over F equal n minus 1 times 1 over R1 minus 1 over R2. And this is the length maker equation for a thin lens, showing you the relationship between the focal length of the lens, the refractive index of the lens, and the radius of the two curvatures. Yeah, so that's why it is the lens maker equation for a thin lens. So we have that because we assume the outer material is air. Imagine now if you sink the lens inside the water. So in that case, this formula changes. Yes, so go home, please find the equation, also the lens maker equation, but not with this assumption anymore. But now it's a surrounding material, and A equal NC, like equal to N prime, for example, like or we say like NA and NB. We have two cases, NA here and NB here, and C is the same as NA. So finally, what do we have? Yes, and this is it will be also one equation for your test. Okay. Yes, what I just mentioned is that we have this lens maker equation. If you have N is the refractive index of the lens material, and 1 is the outer material, is 1. Now imagine its surrounding material is not air anymore, but another type of material. So what is the lens maker equation? Yes, I leave this question for you. And I hope that you will feel awake after receiving that question. Now we have one small example, and this one we will do together a bit. This example is asked us to determine the focal length of a lens. Suppose the absolute value of the radial curvature of the lens and its surface in this following figure are both equal to 10 cm, and the refractive index of glass here is 1 over 52. So I also told you the glass, normally the refractive index is over 1/5 last time, right? So here is one case. They ask us what is the focal length of the lens. So very important, we have that kind of lens maker equation. The difficult task is to find R1 and R2. What are they? So we have already provided you that the absolute value of the radial curvature of the lens surface also equal to 10. So R1 and R2 both equal to positive 10 or negative 10 or positive and negative. So please look at this figure. I will analyze with you and keep in mind the side rule. That's why I really want to precise you. So here we have center as a curvature, and here is a curvature. So you've got C2 and you've got C1 is here. So you've got the radius of curvature of first surface R1 and radius of curvature of second surface R2 is here. PQ is the image, and then finally you found the object PQ, and here's the image P prime Q prime. Here is S and here is S prime. So you got S and S prime are both positive because object is on the same side as the incoming rays to the surface, and image also on the same side as the outgoing rays. Right. So okay. Now we consider R1 and R2 prime. Sorry, R1 and R2. So we look at R1 and R2 here. So R1 center of curvature is on the same side as outgoing ray. Right, so you get what R1 is positive, or R1, yes. So you see R1 is positive because C1 on the outgoing side of the lens. However, R2 is there because C2 is there, sorry, C2 is there. So R2 is negative because C2 on the ingoing side of the lens. So that's why I told you again and again, please remember about the side rule. So that's why you have R2 is negative. You just apply the formula, the lens maker equation, not so difficult to remember. 1 over f equals n minus 1 multiplied by 1 over 1 minus 1 over 2. The tricky part is to replace the right values here. Yeah, so please keep in mind the side rules and what I just analyze with you again and again. Yes, so that is the answer. You understand the result now, right? And also, one remark here is that we find this formula, the lens maker equation, with this kind of assumption. With this kind of assumption, very important. Imagine now, if not N equal and C equal to 1, but like in water, for example, please think and find the focal length in that case, how it changed. Yes, so this is the task for you. Okay, now we see the graphical methods for lenses, very easy. We have two cases for converging lenses and diverging lens. So these three rays of line, yes, parallel to the optic axis, will pass through the second focal point here. Parallel will pass through the second focal point. So pay attention. The second focal point for the diverging lens is here. So it goes like this. So diverge. The rays pass through the center, go straight. Passes through the center, go straight. The third rays passes through the first focal point here. So first focal point is here. Here, the first focal point is here. It cannot pass through. It just like seems to pass through this first focal point, and it goes parallel to the optic axis. Go parallel to the optic axis here, and then you see the intersection point is the image formation here as well. Okay. Array parallel to the axis, array parallel to the axis, here. Emerge from the lens in a direction that passes through the second focal point at 2 on a converging lens, or appears to come from the second focal point of the diverging lens. Do you see? Appear to come, because it's not really right. That's why I use a dash line. You also please remember to use a dash line. It is not really. Array through the center of the lens. Array through the center of the lens. Emerge at essentially at the same angle which it enters and along essentially the same line. So just go straight. Okay. Array through the proceeding. Array through or proceeding toward the first focal point at 1. You see here, it's not true reality. That's why we say proceeding toward the first focal point at 1. So it emerges parallel to the axis. So very clear, right? Yeah. Through the first focal point and then parallel to the axis, and here proceed toward the first focal point, emerge parallel to the optic axis. So just the difference between these two kinds of lenses, so pay attention. Here the overall, because you can have different position and different position of the object. So different position of the image form. And normally you will have the relationship between F to F or something like that. So that's what. We have one example, however, for sure we will do later. Hey. Now we go to the camera with eyes and etc. So this part will be quick as well. Are you tired? Ok, chúng ta sẽ dừng 5 phút học vào lúc 3 giờ nha.
Nó vẫn sống kìa. Ui giời ơi, quá easy. Top 8 à? Có 1. Bài cay sao 3 sao phun đồ. Lại anh tí à.
Tôi chưa bao giờ gặp và tôi chưa bao giờ chụp được cái ảnh mặt cong. Tôi chưa bao giờ chụp được ảnh mặt con mèo nó cong ấy, khó chịu cực. Phải nói nữa là cột đâu.
Chandomini là một bản rất là lãng mạn, rất là đẹp.
Nhưng không thành
hay
công
dùng trong các đám cưới, nhưng mà cái gì nhỉ, gọi là sự sự tích của nó thì không phải là dùng một viên soi hoặc là một bản. Cô nhớ trước cô thấy cái bản Campanella rất là hay, bản cũng rất là đặc sắc. Cô thích nhất cái bản của Kissing này. Campanella.
Bài hát hay nhưng mà
Okay, so now we will move to the cameras. And what we are going to study is like in terms of the geometric optics. So we will simplify all the devices into the optical device. And you will see the cameras or our eyes, the magnifier, the telescope, the microscope. Yes, also they are constructed from the basic optical device is the lens. So we see here the cameras, and the name of the cameras from the Latin word is a room or enclosure. So that like you have like some closed surface, the closed room. You see. So it consists here. You see, you have this object, and through the camera it will form you an image. So it consists of here, this part, a conversing lens. And you have a subtle, yes, so elements of the lens here. Yes, so you say like the body and also the lens. When you talk about the cameras, the body part and the lens part, you have the shutter to open the lens for some duration of time as you want. And you will have a place in which the image will appear. So nowadays, for the modern cameras, you have the CCD, the charge coupled device array. Or before you can, or even now you also sometimes in the photographic film, but before it was the photographic film. Yes, is what we have. And you will picture, you can have the different kind of the viewing site you want, depending on the changing of the focal length. So here, short focal length, longer focal length, and very, very long focal length. Yes. So showing you see? Yeah, here. This focal length 28 millimeters, for example. You see the degree here, 75, 25, and 8 degree. In order to take the image of this size in this statue, for example, so you can observe like a wider or narrower range. So that's why you can have here. And it's showing you in this picture. The larger the value of f, the smaller the angle of view. You see the corresponding. And sometimes you can have the tele, very long distance, right? You have that. So a lens of the long focal length, or we say the telephoto lens, give a small angle of view. You see, and a large image of the distant object. For example, this case, you see, very small angle of view. For example, here we already know 8 degrees, and you can observe a large image of a distant object, but far away. That's why it's called tele. Okay. And the lens of short focal length gives you the small image but wide angle view. So this is called wide angle lens. And the same, what is the lateral magnification in this case? It is a lens. So you just follow the previous equation. You use m equals y prime over y equals minus s prime over s. So if you understand all the path from 2.1 to 2.4 clearly, for the cameras, for the eye, for the magnifier, telescope, you will feel very easily. But it's just a system of the lens. That's all. Yes. Okay, we have one concept which is f number. So the f number here, we have the definition. The light gathering capability of a lens is commonly expressed in terms of ratio f divided by d, which is f number. So we have f and we have d. So what is f? Focal length. What is d? Which is the some kind of diameter. So you have f number equal to focal length divided by the aperture, and we have f over d. In which d, okay, f I just explained, d is a diameter of the adjustable lens aperture of the diaphragm, which is nearly circular hole. Yes, you can have this value. For example, we have F and G, you can find the value of F number. Yes. And the light intensity reaches fifth must be proportional to the square of the F number as well. We are using the projector. You see here, the projector. You have the two lenses and the projectors. Also, and here we have the system of the lenses. Yes, that is what is the application of the lens we have. So easy for the cameras. For this example and the next example, you will do it them yourself. Okay. Now we will move to the eye. For the BEAT, the biotechnology drug discovery, you are in the field of the biology. So I won't teach you the eye in terms of the biology, but in terms of optics. Yes, so you will see how the eye is constructed in terms of the optics. So in this picture, you see the object in front of the eye when change, you can say, that into an image, because we have here also this part, which is the crystalline lens you see here. So step by step, we will see our eyes in terms of optic view. So our eyes is more or less a ball, and it is around 2.5 centimeter diameter sphere. So it consists of the cornea, and the cornea, very important, pay attention as well, because if it is curtain, you can have like some very difficulty in your eyes. My mom, for example, got some problem with the cornea, and we need to use a laser to fix that. And normally they use the green lasers also for the treatment to heal your cornea. So cornea is a tough and transparent membrane. So you got the cornea here. You have the aqueous humor. Yes, this aqueous humor. The reflective index more or less similar to water. So which is the liquid region behind the cornea you see here. The crystalline lens, so which is a capsule containing a fibrous jelly part at the center and progressively softer the outer portion. And then you can have the ciliary muscle in order to encircle this. So you can have the adaptation with your eyes in order to use that. You have the vitreous humor. Yes, we have the vitreous humor as well here, this part. Also, the refractive indexes of the aqueous humors and the vitreous humor more or less similar, and similar to the refractive index of water, around 1.336 here. And the crystalline lens you got here, yes, which is not homogeneous, refractive index around 1.437. And behind the lens, we have the iris filled with thin watery jelly. So you have this different materials as well, and different elements of the eye. And pay attention that most of refraction, light entering the eye, occurs at the outer surface of the cornea. Yeah. And we can form the real image. Yes. We have the refraction at the cornea and at the surface of the lens, and then we can form. Where is this? Where is the image formed? If you want to observe something clearly, the image must be formed at the retina. That's why you have the retina screen, retina here. Okay. We move to the retina. So the image is formed on the light-sensitive lining the rear inner surface of the eye. So it acts as the film of the camera, or the screen where you can store or capture the image. And we have two types, the rod and the cones. Yes, and for sure, you see here we have the SCM, the scanning electron micrograph SCM, showing retinal rows and cones in different colors, in green and blue here. And then it will send the signal to our brains in order to read the information. And we have the foveal centralis, which is very strong, around 0.24 25 in diameter. And you have the iris, which contain an aperture with variable diameter called the pupil. And then they can check the pupil in order to see if you are blind as well. Yes. And you have one mechanism which is called accommodation. The eye, we can look at different distant objects, and then you can use the accommodation in order to adapt, in order to observe clearly that object. So the eye adjusts to different object distances as by changing the length f of its length. So the focal length can be changed using the muscle also. Yes. And pay attention, the length to retina distance S prime does not change. That means the image must be formed exactly at the location of the retina. The reason why me or some of you use that kind of glass, because the shape of your eyes, the place of the retina and the image is not the same. That's why you need some correction lens to support you. Okay. Yes. An object at infinity is sharply focuses when the ciliary muscle is relaxed. That's why sometimes you should free your eyes by looking at some very far away object. And if you move an object closer, now the tension in the ciliary muscle, so the length increases. So that's why you need to change your eyes in order to observe that as well. And when you change that, you see the focal length change also. You have the concept of far and near point. So we cannot observe everything. We cannot see everything in front of you. You have just a range that you can see the object clearly. So we have the concept of far and near point. So the extremes of the range over which distance is possible. And you have, for a normal eyes, the far point is infinity. At the near point, you remember what is the distance. You have here the far point, or sometimes you say CV, right? CV. And for the near point, you say CC. So CC for a near point for a normal eyes is 25 centimeter. Yeah, 25. But for some people, you can different. And the near point depends on the ciliary muscle, how they work in order to make you accommodate with the object. And if you are getting older, you will have the near point of your eye will go further. So you have here, when you have this age 10 to 60, you see the near point gets further here. Okay. So that is the so-called presbyopia of the eye. Yes. In which the near point recedes with age because of crystalline growth throughout a person's life. So that is the muscle change. So you have this further near point like this one. And now we will move to one important part of the eye. It is the defects of vision. So if you have a perfect eyes, that means you can observe from 25 centimeter to infinity. However, for some people, it does not happen that way. You can have some, we say like the defects of vision. So first is the myopic, or we say the nearsighted eye. So we see, for the normal eyes, if you observe some very far away object, the image is formed exactly on the retina. However, if you have some difference in the shape of the eyeball, and then you see that the image is formed not exactly on the retina anymore. So, in the case the eyeball is larger than the radius of curvature of the cornea, so in that case you cannot observe some very far away object. Yes, you see, if the cornea too sharply curved, and then you see the rays focus now on here in front of the retina. So retina
Có
is
trải nghiệm
here,
cái này.
but
Mày đã trải nghiệm.
the image forms here, so you cannot
Nghiệm
observe
mày
that.
không nghiệm. Đó
So it is the so-called myopic eye. So I think a lot of you got this kind of problem, myopic plus astigmatism as well. So the rays from an infinity object are focused in front of the retina. So
Tao
we
mới bị
need
ISU từ cái hồi
we
Covid
need to
rồi.
fix this problem, right? So the most
Thì
distant
học
object for
hồi
which an
Covid này tao
image
bị
can be
ISU.
formed on the retina is not at infinity anymore, but closer
Hồi đi học
than
căng đấy.
infinity. So
Hồi
that's
đi học
why
từ
it's called myopic eye.
giờ thì
And in order to fix that, we will use
12 giờ tối thì cô Lý khỏe lắm.
we will
Cô
use
Lý cô dậy từ
a tool in order to
cô
correct
dậy
that.
từ
That means here we will use a diverging
cô
lens.
dậy từ 9 giờ tối à? Từ 9
In
giờ tối
order to
12 giờ.
make the image closer
Và
to
cô có thể
the
dậy phía
actual
thẳng ngày
object,
trong
and you can observe
tuần liên tiếp
that. Here, the distance
và nhiều tuần
is
liên
here.
tiếp.
And with the myopic eye, the image is formed here, not on the retina, so you cannot observe that. So what we need to do is that
Đấy là
we use this lens, this diverging lens.
lý do là tại vì cô
This
đẻ hồi năm
object,
lớp 11 xong rồi
which
thì
is
cô
distant
nghỉ đẻ
running
xong
very
rồi
far
sao
away.
cô
At first, it will
cô lớp
be, it
khác
is
dậy
the object of
xong rồi cô
this
kia cô kiểu mày đợi
diverging
đợi
lens first.
cô
So
kia cô
the
nói một
image
câu
is formed
cô
here.
sai công thức 3
Then
đến
it
4
will
lần
become the
và
object
xong rồi cô lại nói xin lỗi một buổi có một câu giải cô phải xin lỗi được khoảng 5 đến 6 lần
And the diverging lens
nhiều
creates
nói chung là
a
tao bị
virtual
chán lý rồi
image
từ
that
cái hồi lớp
is
11
inside the eyes.
đã là ngu lý rồi học lớp 10 ra bắt đầu bật lên được tí lại học lớp
The
11
region
hiểu cái
you
này
can observe.
hiểu thì
Then finally, the image is formed.
xong rồi đấy thế là lên lớp 12 thì cô
So
quay
we
lại
will
thấy lớp
find-
ngu lý vậy
Yes, the image is
cô
formed
bị
on
ngại
the retina. We
thế là
will
cô
find
quyết
the-
định là cô sẽ dạy cho bọn mày thành chân lý
We say that the focal length of the glass later on. Second case is a hyperopic, or we say fast-sighted eye.
cho là cô
So
khỏe
for the normal eyes, this
người cô
rays
gầy
from this
như cái thằng
object
bên cạnh
focus on retina.
nhưng mà cô khỏe gấp thẳng đấy
However, for this, we see
căng thật
the image of the distant object is formed after or behind. Here. So in this case, the eyeball is smaller than the radius curvature of the cornea.
không hẳn
Or we say the cornea is not curved enough.
đấy
That's
mày
why
đợi quả
the
vừa thấy mày
rays
lấy rồi
from
thì
object at infinity
một
are
quả xưa này
focused
cũng làm cho mày bay
behind
vào
the retina. So cornea is not curved enough in this case, so the rays focus behind the retina. And for a
lăn
hyperopic
xong rồi
eye,
dậm chân đi
hyperopic and before it's myopic, you just need a converging lens to form and also virtual image at the beyond the viewpoint here. So you use a converging lens. Okay, you form a image here first.
theo đường link vào đây rồi.
Yes, a virtual image at or beyond the eye's midpoint, and then your eye can observe that object to form the image right at the cornea. It is the system. Yes, the image now formed on the retina. And we will see right after how we can use that kind of glasses or lens. And we have another case is astigmatism eyes, and also I have the effect of both myopic plus the astigmatism eyes. So what happened for this kind of eyes? In fact, in this case, the surface of the cornea is not spherical, but it is more sharply curved in one plane than another. So we can see that the horizontal lines may be imaged in different planes from the vertical one. So you see two directions, vertical and horizontal one. And then because of the shape of the cornea, so it makes the image now, yes, vertical here, but horizontal there. So you will see the object look strange. Yes, this one. So the shape of the eyeball or lens causes vertical and horizontal one focus on different
nghe tao nhớ
positions
tao
of
học
the
Việt Quang
patient.
hơn là
So that we can see the change of the shape of the object. So in order to fix this defect, you will need a cylindrical surface here in order to make the object in the same shape as well. Yes, it's what we need to do. We use that to keep one direction the same, but another direction we make it change and then at the same position. Okay. So we use a glass to fix your defects, and in that case we need to check the focal length, and then you see also the spherical power, the cylindrical power for analysis, and be able to describe the orientation of the cylinder. This is for the case of plastic. And we always define the power, how you say the diode, how many diodes, positive or negative, depending on diverging or converging lengths, right? Yes, and pay attention for the power. It is the reciprocal of the focal length, but you must use the focal length in terms of meter instead of centimeter. So define the reciprocal of focal length expressed in meters. And the unit of power is L. Yes, is what we know. For example, if you have a lens with a focal length of 0.5 meter, so the power is 2 diodes. If the focal length is minus 0.25 meter, you will have the power here minus 4 diodes. I will discuss with you these two examples. Here is that we need to correct the far-sightedness. We have the near point of a certain hyperopic eye is 100 centimeter in front of the eye. So you know that for a normal eye it's just 25 centimeter. But here, for a hyperopic or a far-sighted eye, it is like 100 centimeter away, so very far, right? They ask us to find the focal length and the power of the contact lens that will permit the wearer to see clearly an object that is 25 centimeters in front of the eye. So, we need to use here the converging lens, and a hint is that they ask us the contact lens. So the distance between the glass and your eyes is 0. The contact lens is 0. So, for the contact lens, you have here object first, the contact lens and your eye here. This converging lens have to form an image here, the virtual one, and then you can observe this one. So what you need to correct for this eyes is that you put an object at the normal position of the near point, 25 centimeters. Without this converging lens, for sure you cannot observe that, because this eye can only observe an object which is 100 centimeters far away. Yes, you see. So that's why they use a converging lens to form the image here. And this image becomes the object to the eye, and the eye can observe that. So, for the converging lens, D equal to 0. D means the distance between the converging lens and the eye, because the eye has the crystalline lens, as I just described. So you can use your way. However, normally I will use this kind of diagram. The object at the distance S1 equal to 25 centimeters before the contact lens. So it forms the first image. So we can say image 1. And this first image becomes the object to our eyes. Our eyes is the second lens, right? So you got image 1 as 1 prime, and object 2, it is the object to our eye, so it is object 2 with S2. And the relationship between S1 prime, the first image of the first optical device, And the second object for the second optical device is that S2 equals SD minus S1 prime. Or you say S1 prime equal to D minus S2, the same. And S2 must equal to 100 centimeter. You agree? So that this eye can observe. So when it becomes the object to the eye, to this eye, the image is formed at the retina, so that you can observe. So we have, yes, the contact lens D equal to 0, because the distance between the contact lens and the crystalline lens of the eye is equal to 0. Yes, the contact, that's why it's contact lens. So we got the object distance S equal to 25 and the image distance S prime. Here we just use for the contact lens only. You can ignore S1, S1 prime, S2, S2 prime. You just focus like S and S prime. But I use the full diagram to explain. So you use 1 over S plus 1 over S prime equal to 1 over F, and you can find F equal to this value. Okay? And in order to find the power, we will have the power, or you can say D equal 1 over F equal to, you will need to convert this into meter. So it is this value. And then it is equal to
một mình nó là chiếm 2 ô.
It is one example for the correction of the for the five side this. And before we stop, I will discuss with you the nearsightedness as well. So here we have the case in which the eye cannot observe something very far. So in this case of the eye, we have the far point of a certain myopic eye is 50 centimeter in front of the eye. Instead of the normal one is infinity, right? So they ask us to find the focal length and the power eyeglass length. So now it's not contact lens anymore, but the eyeglass. That will permit the wearer to see clearly an object at infinity. And assume that the lens is worth 2 centimeters in front of the eye. So in this case, we see here, okay, we will use a diverging lens in order to help this eye to observe something at infinity, because this eye can only observe something at 50 centimeters only. Yes. So in order to observe something far away at infinity, you need to use this diverging lens so that it can form an image at this point. So which is 50 centimeter far away from the eye. So I use this diagram to describe object at infinity. Through the eyeglass lens, you have the first image, and it becomes the second image to your eye. And your eye can observe 50 centimeter. And D here is the distance between the diverging lens and the eye, which is 2 centimeter. Okay, 2 centimeter here. So for the eyeglass lens, if we now forget S1 prime, S2 prime, etc., you have the object distance S equal to infinity. The image distance S prime equals to D minus S2. So 2 minus 15 equal to minus 48 centimeter. So you can find the F, the focal length equal to S prime equal to minus 48 centimeter. And the power just convert from centimeter into meter of the focal length, and then find the value of the power. So now you understand how you can correct the myopic and hyperopic eyes, right? Yeah, I hope so. In fact, today we should finish this chapter. Is what we expect. However, we will continue next time. We will continue next time for the magnifier. We have magnifier. Always. Do you have another course after this course?
No.
Yeah. Okay. We stop the class right now, and next time we will study the magnifier, the microscope and telescope, and then we finish the chapter. We will go to the next chapter as well. Okay, we can stop here.
Hết quay rồi không?